Hi, and welcome to Week 2 Lab. What we'll be doing this week is going back to our old friend, aspirin, and looking at studying the decomposition of a pure aspirin sample with respect to time. And of course, again, we're going to be looking at some things like aspirin, when we add water and heat, can get decomposed into acetic acid and salicylic acid. And from last term, we all remember this fun stuff. So again, we're going to be monitoring this reaction here, whoops, as we get our pen right, by looking at the salicylic acid. Now, in class, we've been talking about monitoring rate, and so this is our rate law. And our rate law, remember, is going to relate to some rate constant for that specific reaction times the concentration, the molarity, of the reactant, which in this case is the aspirin, raised to the nth power, where n here is going to be the order of the reaction. And so remember, with order, this is telling us the concentration dependency of the reaction. For example, if we have aspirin to the first order, if we were to double our concentration, we know that our rate would double. But if we had the aspirin raised to the second order, if we were to raise or double the concentration of our aspirin, then we know that our rate would go up by a factor of 4. So knowing the order of the reaction will be important because it talks about then, or will explain, the concentration dependency of our rate of decomposition of aspirin. Now, as in class, what we have looked at is our rate, of course, is going to be, of course, the change, okay, in the concentration of aspirin over the change in time. And remember, here we have a negative sign because this is a reactant. And that's also going to be equal to the change in the concentration of the salicylic acid over time. And that's a positive number because that's a product. And so we'll see that they are stoichiometrically related because this is a 1-to-1 ratio in our reaction. So essentially, we can be talking about how fast is the aspirin decomposing if we were to measure how fast we get the appearance of the salicylic acid. Now, the salicylic acid, like in last term, is going to be complexed with iron, okay? In our case, iron chloride, and the iron ion is just surrounded by roughly about 6 water molecules. And by adding this pale yellow iron complex, it will bind to the salicylic acid and create a purple molecule. And of course, then we can look at the interaction, or how much purple do we actually have. And of course, we'll use that using visible spectroscopy, specifically using the SPEC 20, to determine the concentration of the purple salicylic acid complex. Now remember, back to visible absorbance theory, is that if, let's say, we have 100% of light at an intensity passing through a cuvette with a colored compound, that only a certain amount of the energy will pass through the cuvette. And so we will have less intensity because some of the light passing through the colored substance is absorbed. Okay, and so we are going to be looking at, we could either look at the percent transmittance, how much does the amount of light being transmitted through the sample change, or in our case, we're going to be looking at absorbance. Essentially, when the light is coming in here, and let's just get a different color, if we're looking at our salicylic acid iron complexes, as the light is coming through, these colored molecules can absorb some of the radiation, okay? And so our absorbance then is measured how much is being absorbed. And of course, we can relate that to then concentration, because the more molecules of salicylic acid that are present in the sample, the more energy will be absorbed. Now, before you come to lab, there are a couple things that we need you to do. You will need to prepare data tables and write your purpose in your lab notebook. Okay, and make sure that this purpose is at the top of the page. Make sure you put your full name. Make sure you're putting your lab time, okay, in the locker box, okay, 9:30, 1:30. Also, write down Chem 163 up there, and then, of course, the entire title of the lab, and this is experiment number 2. Okay, you can't put your partner's name in yet because, of course, you don't know who your partner is for this week. But I would prepare data tables. If you need a sample of this, of course, look at Canvas. And there's a file in Canvas that says lab, notebook, criteria. Okay, and so in there is a sample way to set up your labs. Now, you do want to familiarize yourself again with the Spec 20 operation, how to set the transmittance to 100% and then the absorbance to 0%. Okay, and so there are a couple of different movies. Okay, and again, how to find unknown concentrations using the Beer-Lambert law. And so I will actually be doing the calibration curve for you before you come to lab. And so I will actually give you the calibration data from some known salicylic acid solutions so that we don't have that part of the lab to do redo again. We did it last term. I'll give you that information. Now, when you're coming in to measure the rate of the reaction, we will be doing 3 different decomposition reactions. They're all of aspirin, but they're at different experimental conditions. And so what we will do is we will have 3 different test tubes. Okay, so number 1, 2, and 3. And number 1 and 2, what we will do is we will change the concentration of the aspirin and see how the rate changes. So in class, remember, when you change the concentration of the reactant and see how the rate changes, you can find the order of the reaction from that piece of data. And that's what we're going to do. Then what we'll do is we'll also look at comparing trials 1 and 3. Now in 1 and 3, they will have the exact same amount of aspirin in them. But what we will do is we will change the temperature, okay? And so by changing the temperature, we'll see how the rate changes with respect to temperature. And something that is temperature dependent is the rate constant K. And so we can determine then the rate constant by looking at how the rate changes with temperature. Now, the first thing you will need to do is, with your partner, you'll each have a large beaker, and one of you will make up a hot water bath, and the other one will use your beaker to make up an ice bath, okay? And so with the hot water bath, we need this to be pretty steady, okay? And so you may have to spend some time with your hot plate adjusting the dial, essentially, to get it to keep your temperature steady around 80 degrees. And it needs to be steady at 80 degrees for at least 5 minutes. Okay, we do not want the temperature varying because, again, if you vary the temperature, then you're varying the rate. And we don't want to vary that temperature until trial 3. Okay, one of the things you may do is put a magnetic stir bar in the bottom of your beaker of water. And this water can just be tap water. And turn it on a slow, gentle spin. If you can hear the magnetic stir going clank, 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 it's too fast. Okay. So the other partner will make up a ice bath, and then you'll get 3 test tubes labeling them 1, 2, and 3. And you also want to label them with what chemical is in the test tube. So again, if some, God forbid, accident could happen and you keeled over in lab, we know what's in the test tubes. So please label them as aspirin. Now, you will be weighing out different amounts of aspirin into your test tubes. And so test tube 1 and 2, this is where we are going to be changing the concentration of the aspirin. And then test tube 1 and 3 will actually have the same exact amount of aspirin in them. We'll just be varying the temperature. Now we do want to weigh out about 60 milligrams of aspirin. And with that, we do want to be very careful to not really exceed a wide range of that, because again, we want to make sure that test tubes 1 and 3 have relatively the same amount of aspirin in them. Now you do want to record the exact mass. Now don't spend all day trying to get exactly 0.060. It's not going to happen, but you can have it plus or minus that 5/1000ths of a gram. Then you'll add that to test tube number 1, and of course try to transfer all of the sample to test tube number 1. Okay, and I would weigh this out probably on weigh paper because putting chemicals into the test tube and then trying to get it back out again is very difficult if you overweigh. If you get too much mass of aspirin, do not put it back into the stock bottle. Okay, that will contaminate it. And so if you have extra aspirin, see if anybody else needs it, or throw it into the aqueous waste beaker because people will be throwing water in there at some point. Just throw it away in the aqueous waste beaker at the end of one of the tables or benches, and that's what we're going to do with the extra. Do not put it back into the bottle you took it from. Now, what we'll be doing is you will want to make a data table in your lab where you will be measuring your exact masses. So for example, I as a student then measured out exactly this many grams. And of course, in your lab, include units, or you could have said, you know, up here, this is how many grams we have. But again, here, this will have units of moles, and this will have units of molarity. And so make sure you're putting units on your numbers though, because I will check your carbons for that, and of course your end results when you hand in your data. So for each of your trials, put in your exact mass. Now with that exact mass, we're going to be using the molar mass of aspirin here. I just used my periodic table that Heather gave me in class. Hi Heather, I'm really good about that. And we can then utilize this to calculate the moles of aspirin, because you know you can take grams then and get moles. And so you need to show this calculation on your calculations page, and of course make sure that you are writing down, okay, your chemicals. And of course then you've got your 1 mole of your aspirin is 180.1598 grams of the aspirin. So make sure you're showing all of those calculations. Okay, and so what I can find here is that my number of moles of aspirin for this trial then is 3.33 times 10 to the minus 4. I'm going to put units on that, moles of the aspirin. Now, we only have 2 significant digits here. Of course, here we have a lot more, 7. There'll only be 2 in this answer. Whoops, my pen is not working. But I'm not going to round that off yet because I'm going to use that information further on, so I don't want to get any rounding errors. So I'll utilize that then to find the molarity. Now, to find the molarity, or the concentration of aspirin at time 0, essentially the initial amount of aspirin that we have, you're going to take your number of moles and you're going to divide it by the volume of solution. Now, in your lab procedure, it says to take the 60 milligrams of aspirin and dissolve it in 10 mils of water, or at least add 10 mils of water. And so here, the amount of water that this is diluted into is, of course, 10 mils, or 0.01000 liters, because we're using a volumetric pipette to add the water to the test tube so that we get more significant digits and a more accurate solution volume. Now, when I do this, I'm going to get then 3.33, only 2 significant digits, times 10 to the minus 2 molarity, and tell me molarity of what? It is the aspirin. And you do need to tell me molarity of what chemical, because that will be really important. Okay? And so over here, again, I'm not going to round this. Now, I used some data from test tube B, and again, this is not indicative of what you would see in your lab. This is just made up stuff. But let's just say I found the molarity in test tube B to be the following, because of course I've changed my concentration of aspirin for my test tube B. So I would have done these exact same calculations and measurements for test tube B, and let's just say this is what I came up with. Okay, 2 significant digits there. Now, as we said, we are going to volumetrically add 10 mils to test tubes 1, 2, and 3. And as we know from last term, it really doesn't like to dissolve in water. And so some of it will float, some of it will stay at the bottom. But we will put our stirring rod into test tube 1, because that is our first reaction rate that we'll be measuring. And we don't want to remove that stir rod until the very end, because we don't want to lose any of the sample. And as we heat the aspirin with the water, we'll see it dissolve. So now in terms of carrying out the reaction, our temperature must be steady at around 80 degrees for at least 5 minutes. Now, if it was at 81, that's totally fine, 82. But we do need to record our temperature, okay, and keep an accurate measurement of that. We'll be using the lab quests, like we did last week, as our thermometer. Now, we will pick up our test tube number 1 then, and as soon as we put it into the water bath, we're going to start stirring it, and we need to start our stopwatches, okay, as soon as that test tube goes into the water bath, because we are applying heat and hopefully starting the decomposition reaction immediately. So I do want you to measure and record the temperature of the water bath at 1-minute intervals. So keep the stopwatch going, but at 1 minute, record what the temperature is, at 2 minutes, and so on, so that we can ensure that the temperature is remaining steady. Now, when you put the test tube in, your temperature may temporarily go down because it's adding a little bit of a cold item into the water bath, but it should pop back up right away. Now you're going to leave the test tube in the water bath for exactly 6 minutes, taking the temperature readings at 1-minute intervals. At 6 minutes, remove it promptly from the water bath and put it into the ice bath. This is where you're going to stop the decomposition reaction. You do want to stir it with your stir rod, okay, to make sure that we're cooling this down as fast as possible. And then as your solution is becoming cool, when it becomes cool, you can put it in the test tube rack. Now here's a table. It's not labeled, but you'll need to label this something similar to this in your lab notebook before coming to lab. But what I have here, up here, is the time in minutes, okay, for trials 1 and 2, because at every 1-minute interval, I'm going to be measuring the temperature. And then I also put up a different time scale up here in minutes for test tube number 3, because I'm going to take the temperature in 2-minute intervals, because in reaction 3, we're going to decrease the temperature of the water bath, and in doing that, we slow the reaction down, and so it takes longer for the reaction to occur. So here is some sample data, and again, not indicative of what you will exactly get into lab, but this was a trial run where I measured the temperature at 1-minute intervals. So using this information then, I can then look at the average temperatures of each of the test tubes. So essentially, you're going to take these 6 data points and find the average of those for each of your test tubes, okay? So I found the average for test tubes 1, 2, and 3, okay? And again, you have to realize that you made up data for these things, but this is hypothetically, what I came out with. I also am going to look at test tubes 1 and 2, because they are roughly at the same temperature. I can average their temperature, okay, and look at this average temperature then, because what I'm going to be doing here is I can also look at test tubes 1 and 2 and find their average rate constant, because they both do have the same temperature. I can measure their rate constant. And so here for later on in the lab, I want to find the average temperature over test tubes 1 and 2. And I do want to, and this is significant to the 8 here, I do want to put this into Kelvin, because later on when we're trying to find the activation energy, this is something we can find from rate laws. How much energy does it take for the aspirin when they collide? What is their minimum amount of energy for a reaction to occur? And so this does need to be in Kelvin later on. So I also put my temperature in Kelvin for test tube number 3 for myself later on in use. Now in test tube number 1, once it's cooled into the ice bath, we can add indicators. So we'll use a 5 ml volumetric flask, volumetric pipette, and add in our iron chloride and of course stir that. And of course we know that this should turn purple. Now, we will be using the spec 20. Please use the iron chloride as a blank, and as with last term, please make sure that you set 0 absorbance between each sample, okay, before moving on. Okay, so between test tubes 1, 2, and 3, make sure you're re-zeroing the machine. Now, the exact instructions for calibrating and zeroing the machine to 100% transmittance and 0 absorbance are found on the top of the machine. If we look at the top of the machine, typically there is an instruction sheet over here that will say step 1, touch this dial. And so, again, you should have watched the video on how to zero your machine. And if you're having problems with that, ask a coworker, ask your partner or another team on how to utilize the spec 20. Now, you do want to condition the cuvette, okay, because we'll have 2 cuvettes, one with your blank. And remember, fill it about 3/4 of the way up, okay? And remember, cuvettes typically have that circle on the top, so if you just fill it to about halfway through that circle, and remember there's a line on there, and you do want to align that line that's on the cuvette with the line that is on the sample holder. You do want to condition your cuvettes with your reaction solution before reading the absorbance. So add a little bit of your aspirin solution from test tube number 1 into the cuvette and just roll it around in the cuvette, making sure all the inside surfaces are touched by that, and then throw that away in aqueous waste. And then you can put your aspirin solution in the cuvette, put it into the machine, and read the absorbance. So I did that, okay, in my fake data, and here is the absorbance of my solution, okay? Now, you will need to then calculate the concentration of salicylic acid found then in each of your test tubes using the calibration curve that I will provide you. So here is a sample calibration curve line. And again, it is not indicative of what you will get in class. So please do not compare this equation of the line to any that you would get in class, because again, I'm making this stuff up. So if you are given this equation, remember Y is the absorbance, X is the concentration, okay, of salicylic acid. And for our calibration curve, the concentration of salicylic acid was measured according to standards where I knew what the molarity of the salicylic acid was. So in solving for X, I find that we get 1.91 times 10 to the minus 3 molarity. Because there are 3 significant digits here, okay, and 3 here, okay, there should be 3 in the answer. There's 3 here. Now there's only 1 here, but remember, because we are subtracting data here, we still get a resultant of 3 significant digits in our molarity. So I have put that here, and we have molarity of our salicylic acid. Now, the next thing to do is, of course, note that the change in the amount of aspirin is essentially the same as the appearance of salicylic acid. And so what we'll find is that salicylic acid appears when, of course, aspirin decomposes. And so we can put that information on the next line. They'll be the exact same number. Now we can do this for test tubes B, 2 and 3, later on, but we're going to continue on with our data markup for test tube 1. Now, once you have measured the absorbance of test tube number 1, that is the last piece of information or data that you actually need to write down in your lab notebook. So once you have finished measuring the absorbance of test tube number 1, you can throw the contents of test tube number 1 into the waste and then move on to test tube number 2. Okay? You can weigh out the sample, dissolve it in, or add 10 mils of water, put it into the water bath, and of course record the temperature every 1 minute interval, and moving down until you record the absorbance. Once you've recorded the absorbance of test tube number 2, again, we can put the contents in waste and move on to test tube number 3. Okay, so in test tube number 3, though, when we get to this point, you will need to reduce your water bath to a temperature of 70 degrees, and we'll move on and we'll talk a little bit more about that, but we will change the water temperature. Now, in your calculations, after you have found the concentration of salicylic acid, we need to correct for warm-up time, because when we put the test tube into the water bath, what we may notice is the temperature of the water bath drops a little bit and then does come back up to the 80 degrees. But we need to correct for that warm-up time. And so what the authors of a particular experiment that I utilized some data from found was if we have the test tube in the water bath for 6 minutes, we're actually going to state that the reaction time is actually 5.5 minutes, allowing for 30 seconds or half a minute for warm-up time, in that the reaction has not effectively started for a half a minute. So you do need to utilize our reaction time then as 5.5 minutes, not the actual 6 that the test tube was in the warm water bath. Okay, now, in moving on with calculations, and again, none of these calculations need to be performed during the lab time. Now, we had made sure that we had our 80-degree water bath. We would make a new ice bath in order to do test tube number 2, and then, of course, repeating all the steps, except with 40 milligrams of aspirin, we would again find, by changing the concentration of aspirin, how does the reaction rate change. Okay, and so we can get that information for test tube number 2. Now, because we've reduced the concentration by half, we'll see how this changes the reaction rate. Now, once we have that data, okay, then we are going to look at finding the following. Whoops, I think we're missing a slide. There we are. We skipped forward, sorry about that. Now we need to find the reaction rate, the change in the concentration of the aspirin over the change in time. Now, in order to do that, what we'll be doing is we, of course, have to have rates for all of the trials, okay? And so I'm gonna show you in test tube number 1 how to calculate the rate. And you'll see here on my slide, I already have data for test tubes 2 and 3, again, using fake data. Now, in order to find rate then, I'm gonna look at rearranging this equation right here, okay? Oops, sorry. This equation right here. So let's go back there. I want to get my eraser because I already jumped ahead of myself here. So sorry about that. I'm going to be looking at this relationship right here. So rate is just going to be the molarity then of the aspirin. And again, because we're using initial rates, we're going to be looking at the initial molarity of my acid divided by the change in the time. And so here I'm going to have, and here's my changing of my aspirin concentration. Now, with the change in the aspirin, what we'll find is that is the same as the concentration of the salicylic acid, because the salicylic acid is appearing as the aspirin is disappearing. And so from the concentration of the salicylic acid that we found from the spec 20, okay, this is the concentration of the aspirin, okay, the change in it, okay, because that is the amount of salicylic acid that we produced, divided by our 5.5 minutes. Okay, and so we will have then molarity per minute. And what I get here is 3.47, and that's got 2 significant digits because of my time. But of course, if you have a more accurate stopwatch, you might have this to 2 numbers beyond the decimal place, and then of course you would have more significant digits than I do. But 3.47 times 10 to the minus 4, and the units on that are molarity per minute. Now you'll see here that I do have fake data for trials 2 and 3. Now in trial 3, remember the time though will be 11 minutes, okay, that we are using as our time factor. But for all of these test tubes, you're looking at the concentration of the salicylic acid that you measured, okay, from the calibration curve after the reaction was done. Now, this then gets us to a really great piece of information. How do you find the order of the reaction? So remember in class, we looked at the ratio of the rate, let's say in reaction number 1 versus the rate of reaction in reaction number 2. How does the concentration change in reaction number 1? How was the concentration changed in reaction number 2? And then that is to the nth power. Now remember, these concentrations are the concentrations of aspirin that we threw into the reacting vessel, or the initial concentrations of aspirin, okay? And so if we look at our reaction rates, if we look back here, here is reaction number 1 and 2's rate. So reaction number 1, 3.47 times 10 to the minus 4. I'm not going to worry about putting units on that because they're going to cancel out anyway. For my fake trial 2, my reaction rate was 1.95 times 10 to the minus 4. Now I do need to look at the amount of aspirin in test tube number 1 initially. So that goes way back in our slides. Okay, back to how many molarity did we have starting of the aspirin. So I had 3.33 times 10 to the minus 2 molarity initially. And in trial number 2, I had 2.19 times 10 to the minus 2 molarity. Okay, and then again, these are initial concentrations. And then of course, this will be raised to the nth power. So what I get here on the left, 1.779 is equal to 1.5205 to the nth power. Now we do want to actually get the n then. So because we have I'm going to take the natural log of both sides. So the natural log of 1.779 is equal to the natural log of 1.5205 to the nth power. Now remember, with natural logs, if I'm doing that, the n coefficient can come out front. So I'm going to take n times the natural log of 1.5205 equal to the natural log of 1.779. And what I get here is n is equal to 1.37. Okay, so I'm going to put out the actual order then, 1.37. And of course, I'd round that to the 1.4 with significant digits. Now, the rounded order, what I mean by that is I want an actual integer. What integer are we closest to? And in this case, we are closest to a first order reaction with respect to any errors and things like that. So right now, we could then write the rate is equal to K times the concentration of aspirin to the first order. So if we double the concentration of aspirin, the rate should double. Now, to find the activation energy, this is going to be looking at the dependence of the temperature on the rate constant. And so this is going to be between trials 1 and 3. So now in test tube number 1, you do have the same concentration as test tube number 3 of aspirin. They're about 60 milligrams. But now we need a new temperature. And so in test tube number 3, we are going to cool down our water bath. So for us, we do want to shut it off or add some ice. I would add ice. Add ice to the water bath to get the temperature down. And I would add a little bit at a time, and then obviously turn the dial down on my hot plate so that we get our temperature to be steady at 70 degrees or around there for at least 5 minutes. Now, as we said, this reaction is going to go more slowly, so we will run it for a total of 12 minutes. And we will take the temperature at 2-minute intervals. We again will measure the temperature every 2 minutes, and then exactly at 12 minutes, we'll take our test tube out and put it into an ice bath. Remember, when you're putting your test tube into the water bath here, time is equal to 0. Start your stopwatch as soon as the test tube number 3 goes into the water bath. We'll cool it, okay, after the 12 minutes, and then, of course, record the absorbance in the Spec 20. We are going to correct for warm-up time, and we're going to give ourselves a little bit more time here in that instead of only a half a minute for warm-up, we're going to give ourselves a full minute. So our time interval here will be 11 minutes, okay? Now, with this data, we can look at the Arrhenius equation that is effectively looking at how do the rate constants change versus temperature. And of course, here is our activation energy, which is, of course, what we would like to calculate. Now, here is again some fake data. Here are the rates of my 3 reactions. You'll notice that these you've seen before on other slides. And then we need to calculate the rate constant for each one of our test tubes. And so that's what I'm going to do on this slide, show you how I did this for test tube number 1. Now, here is our rate law. We now know what the reaction order is. It's 1. We know the rate, and we know the concentration of aspirin initially in all of these trials. So in order to find the rate constant, it's just going to be equal to then the reaction rate divided by the concentration of aspirin initially in the test tube. And so here, our rate that we found for test tube number 1 was 3.47, and the line underneath just is showing my line up here for sig figs, times 10 to the minus 4, and that is molarity per minute, divided by, and again, this is the initial concentration of aspirin going way back in our table here. How much did we weigh out, and what was the molarity? 3.33 times 10 to the minus 2 molarity. So you'll see the molarities cancel, okay, because this is a first order reaction. And what we will get here is 1.04 times 10 to the minus 2, and that has units of reciprocal minutes, or minutes in the basement of a fraction. So I could put that up in there. But I, of course, have some fake data for my other trials. Now, in test tube number 1 and test tube number 2 here, because they were at the same temperature, okay, you will want to find the rate constant, okay, because the rates are different, but the concentration, remember, rate depends upon concentration. So we can use test tubes number 1 and 2 to find the mean value of the rate constant at 80 degrees. Okay, and so all I did was take my values of my rate constant for test tubes 1 and 2 and find the average. So I found with my fake data 9.66 times 10 to the minus 3 reciprocal minutes. Okay, and then of course find the standard deviation. Now I would like you to record the mean to the correct amount of significant digits. For example, if you had a standard deviation, well, first of all, let's just look at what my rate constant here is, average, 0.0966. Let's say my standard deviation was found to be 0.0001. Now, I want to make sure that my mean is rounded to that. So you're going to see that it's rounded to this decimal place. And so we would round it, of course, then to 9.7 times 10 to the minus 3. But if, on the other hand, let's take my eraser here. We found the standard deviation to be 0.001. This would be the last decimal place then I could believe in my average. Okay, even though significant digits said I could go to the first 6, the standard deviation tells me I can only go to that 9. And so here I would have to round up that 9. And so my average K now would be 0.01. Okay, so please be aware of that because we're rounding up the 9 to the next 1 here, and so this would have to be my average. So we're rounding according to standard deviation. And remember, standard deviation only ever has one significant digit. Now, we're ready for finding the activation energy. Now, in order to find the activation energy, I need a couple of pieces of information. First of all, what is the average rate constant for test tubes number 1 and 2? And what is temperature 1? Okay, what was the temperature in test tube number 1 and 2? And so this is my average temperature for test tubes 1 and 2 and put into degrees Celsius. I will need my rate constant for test tube number 3 and the average temperature of test tube number 3 put into Kelvin. This is the R value that you will use in this equation. And so I just need to plug in information. So here I'm going to have the natural log. K2 is going to be the new rate constant at the new temperature, and so that's going to be the rate constant found in test tube number 3. So 4.10 times 10 to the minus 4. The rate constant for test tube number 1 and 2 will be my K1, 9.66, my original temperature, is equal to the activation energy over R, which is 8.314 joules per mole Kelvin, 1 over the first temperature in degrees Celsius, degrees Kelvin, 353.0, that's significant digits, Kelvin, minus 1 over the new temperature, 343.85 Kelvin. In solving for that, I get the activation energy is 3.447 with only 2 significant digits times 10 to the 5th joules. Okay, and you might have different number of significant digits than me because again, remember, I'm making my stuff up. Now I can put that into here then. I'm going to use my rounded answer, 3.4 times 10 to the 5th joules, or this is also 340 kilojoules. Now, in terms of our reaction when we're all finished taking our absorbances, all these calculations we'll be doing at home. All of our products, anything extra, will go into our aqueous waste jugs. And take those jugs up to the front instructor's table when you're all done, because then the instructor can treat the waste. Hand in your cuvettes to the instructor. So physically, you're going to get a little glass jar that has the 2 cuvettes in it that she has given your group. Please hand those back to her. We just want to make sure that those don't get left in the Spec 20s. Wrap the cords around the Spec 20s and put them and return them into the cabinets. Return the Kim wipes. Okay, the Kim wipes are the little pieces of paper tissues that we use to get your fingerprints off of the cuvettes. Please return those to the cabinet in which you got them. Make sure you hand in your carbons and make sure that they are stapled together or you will be counted off, and make sure that you sign and date them. Okay. Now, I only need 1 submission per partnership. Okay, but remember to submit your data by Saturday at 11:59 p.m. Okay, because the instructor will need this information. I will not post the class data for you. Let me look at this. Yes, I will post the class data, on Sunday in the AM. So that you can see how everybody else in the class did in order to find a mean. Now, here is your report form that you will need to hand in 1 week from the day that you perform the lab. And again, remember your lab day and time. That's really, really key here for me. So you are going to be submitting your data by Google Docs. So again, you get points attributed to that. So if you fail to do that, you and your partner will lose some points. So decide who's going to submit it. And if you do find that you make a mistake in your submission, you are allowed to go back and resubmit the data until the cutoff time. And you will have to resubmit the entire form again. Okay, and it will make note of that in the Excel program that it dumps into, that you've just changed your data. It doesn't give me a second trial for you guys. It will just change your data in the form. Now, you'll notice here I want the report form, then followed by the calculations page, and those can just be carbons from your lab notebook. If you are using the carbons, though, please press firmly so that I am able to read the calculations. If I can't see the calculations, you'll have to write them on a separate sheet of paper, okay? Because, again, I need to be able to read those. And then, of course, your post-lab question sheet, which is also found in your lab on Canvas. Now, you're going to be putting your activation energy in here, and remember, we will be stating things to significant digits. So I rounded mine 3.4 times 10 to the 5 joules, or that's the same as 340 kilojoules. And then you're going to want to look at what is the mean. So you're going to want to look at the entire class. Now, you are going to want to make a decision. If you see that there are outliers in the data where most people are getting the same answer, but maybe one group has data that is incredibly different, you can remove the outliers from your calculation. If you do that, you need to make note of that. So if you take out someone's data on your report sheet, you'll say, I took out data point, 22 kilojoules in my calculation, okay? Because, again, it was so far off of everybody else's. So then you'll give me the class mean here. You'll also give the standard deviation for the class. As long as you have indicated what data point or points you have removed from your calculations, then I will know that maybe your class average is different than someone else's if they failed to take out an outlying piece of data. It's your guys' decision on what to determine if something is an outlying piece of data. And then we're going to be looking at finding the percent error in the activation energy. We're going to look at the class mean as the true value for the activation energy then. So remember, percent error from our last lab is the absolute value of the true value minus your value divided by the true value times 100%. And essentially all we're doing is just trying to find the percent difference. And so we're going to see how much yours was off of the class mean. Okay? And so we're just looking at this as, you know, a difference. Now, you will complete then your report form page. Significant digits are going to be important, so make sure that everything has been rounded. It is not okay for you to give me an answer like this with the line above it, because I don't know if you know how to round that off. And so make sure you're writing that if it's going to be 3.4 times 10 to the 5th power, that's what you wrote, okay? Now, you will be showing your calculations, and you can use carbon copies, but you will need to number the calculations. It's easier for me to see them. Name what you are trying to calculate, define the equation variables, and then give an example. Okay? And then, of course, staple in this order: report form, calculations, post-lab questions. So, for example, what I mean by on your calculations. So let's say, whoops, my hand is drawing lines versus my stylus. Whoops. So on my calculations page, I can't write with eraser. Calculation number 1. I'm going to determine the moles of aspirin, because that was the very first thing that I did in this lab. So that's going to equal, so I want to say, all right, what's the equation? That is the grams of the aspirin times 1 over the molar mass of the aspirin. So you'll notice that I have told me of what chemicals and how I'm actually going to calculate this. So I've defined the equation. So then I can put my numbers in. I can say, all right, here's my example. I had the 0.060 grams. The molar mass was 180.1589 grams was for every 1 mole of aspirin. And again, I want to make sure that I am writing down what chemicals, okay? Because you can't say, hey, I owe you 5 grams of something, you know, someone's going to say 5 grams of what? 5 grams of cookies, 5 grams of, you know, aspirin. What are you talking about? Like the next one, I'm going to look at calculating the molarity of the aspirin. And again, you only need to do this for 1 trial. Okay, you don't need to do this every 3 trials. I just need 1 example of data. Okay, and remember, you do need to write down, I got 3.33 times 10 to the minus 4 moles of the aspirin here in the first calculation. Okay, now molarity, then we can take that number. Oops. We need to define it first. My mistake. Bad, bad, bad. Molarity, again, is moles of the aspirin divided by the volume of the solution, and that's in liters. And then, of course, you can use your sample data and get me an answer. Okay, making sure that you have molarity of aspirin as the unit on your end answer. And again, worry about significant digits and units. But please number them. It's easier for me to see. And then, of course, tell me what you're looking for here. Define your variables. In this case, we have variables here. Okay, or if, you know, in our EA over R, you're going to have to say R is the gas constant, EA is the activation energy, the ln of K2 over K1. What's K2? What's K1? All of these things need to be defined. And so you can do them as a list. Okay, so for example, on the activation energy equation, the Arrhenius law, whoops, the Arrhenius equation. So hold on, let me erase a couple things here. Here you can give us a list. K2 is equal to blah. K1 is equal to blah. EA stands for blah. R is equal to blah. So you can write out, this is the rate constant, the new rate constant, the old rate constant, the activation energy, the universal gas constant, the new temperature T2, the old temperature T1. But define every term in your equation before plugging in numbers. Now, you'll be handing in your report form sheet, your calculation pages, and then your post-lab questions. If there's room on the sheet, you can then hand write in your answers. And you can use pen or pencil, doesn't matter. But remember, significant figures count, okay? And of course, units. And so you want to, if you run out of space, you can add additional pages if needed, of course, on the back. And make sure that you have stapled this thing before coming to lab, because in lab, only going to allow a couple minutes for people to hand in things, because then we do need to get started on the next new lab. We don't want everyone trying to get all their pages and things organized. Please come with organized, stapled lab reports so that you can just come in and stick it on the pile. We don't need all of this, everybody frantically looking for all their pages at the beginning of lab. It's not very professional if you're coming into your boss going, oh, I have a page over in this handbag, but oh, I forgot this page, as he's waiting for you to hand in a report for your job. And so we're trying to get you to a point of which we're going to be professionals and hand in our report in one fell swoop and allow the instructor to start in on the next new lab. If you have any questions, remember, I have 5 office hours during the week, 2 on Tuesday before labs are due. And so if you need to, please email the instructor, me, or come to an office hour, because those are great. And some of the office hours are group office hours, or bring a friend. So if you both have the same questions, we can get those answered. All right, I hope that you guys have a good weekend, and I will see you guys on the next Tuesday. All right, we're all done.